So this video is going to focus on interpreting proton NMR spectra. I've said proton NMR, even though it says hydrogen NMR here, because that's sometimes what hydrogen NMR is referred to. So you need to be just familiar with the fact that it can be called proton NMR, and if you see that phrase, then they're talking about hydrogen NMR. So my overall aim in this video is for us to be able to interpret spectra like this, for us to be able to deduce the structure of the molecule that's responsible for this particular spectra. So if we're just thinking about what information we have, let's forget the fact that we're actually interpreting it. We have these peaks, and they are called signals. So what we've got in this particular spectra, highlighted with green, are 4 signals. So they are, or I'm going to refer to them as hydrogen environments. So they are unique hydrogen environments, which I'll explain a little bit more in a short while. Another piece of information are these values. So they are integration values. They're essentially a measurement of the area underneath those peaks or those signals, and they give a relative ratio of the number of hydrogens in each of those unique environments. The next piece of information we have is how many lines there are in each of those signals. So remember, the signals are what I've highlighted in green. So if we work from left to right, then this signal has just 1 line in it. The second has 4 lines in it. The third has 1 line in it. And then the final one, the one on the right, has 3 lines in it. So we would refer to starting from left to right again, we would refer to the one on the far left as a singlet, the second one as a quartet, the third as a singlet, and then the final one as a triplet. So we're going to understand why that's happened. That's something else that we're going to consider. And then the very final thing, or very final piece of information, is if you look along the bottom, there's a scale, and this is called the chemical shift. If you look at your AQA data booklet that you get for the final exam, on page 3, which has the infrared spectroscopy absorption values, it also has the proton NMR or hydrogen NMR chemical shift values and the carbon-13 NMR chemical shift values. So I'm going to assume that for the rest of the video that you have that data sheet or that page to hand. I'll still be referring to it and trying to explain bits, but I'm afraid I can't show you the data sheet at the same time that I'm working through a particular problem. So it's going to be to your benefit to have that to hand. So let's unpick some more what we mean by hydrogen environments, which means therefore number of signals, what we mean by the integration values or the number of hydrogens in those environments, what we mean by the splitting patterns, and then finally what we mean by the chemical shift. So I'm just going to draw an example molecule. So I've kept it fairly simple to start with. So let's have a look then at how many unique hydrogen environments there are. So I'm going to identify them, and then I'm going to explain why I've said that. So the methyl groups are the same in this molecule. To me, they are identical hydrogen environments. And then the 2 CH2s next to them are also identical hydrogen environments. So I'm saying that if we were to get an NMR spectra, hydrogen NMR spectra for this molecule, we would have only 2 signals. So why is that? So when we look at this environment, we've got to think, I think one way of thinking about whether hydrogens are in the equivalent environment or not is to think about their geography. So if I start from here and I look at what's next door, I've got a CH2. And if I look at what's next door to that, it's a CH2. And if I look what's next door to that, it's CH3. And if I start from the opposite end, what's next door to that? CH2. What's next door to that? CH2. What's next door to that? CH3. So for me, these both have exactly the same geography. And in fact, I can sort of show this a little bit more clearly, but you do have to be a little bit careful about this because you have to think about how a molecule is being drawn. But there is a very clear line of symmetry down the center here. So when I look at those two methyl groups, they are mirror images of each other in the way that this is drawn. They are equivalent to each other. There is nothing to differentiate them. There is no difference in their surroundings. There is no difference in their geography. And that is also the case with the CH2s. So that would explain why we got different signals. If we think about now that integration value, or the ratios of, or the numbers of hydrogens in the different environments, we've got two environments, so they are highlighted green and yellow. And in the green environment, I've got 6 hydrogens, and in the yellow environment, I've got 4 hydrogens. Now, when you're doing ratios, you always, in maths, you're always trying to get the simplest form of that ratio. So I could simplify that. There's a highest common factor of 2. So really, my integration value ratios are going to be 3 to 2. The next thing then is how do those two signals split? Or how many lines, are in each of those two signals? So are they a singlet? They have 1 line. Are they a doublet? Do they have 2 lines? Are they a triplet? Do they have 3 lines? Are they a quartet? Do they have 4 lines? In AQA, I've never known them to go beyond a quartet. So if we're looking at the green signal, then what we have to do is we have to look at what's adjacent to those, or to that environment, and count the number of hydrogens that are attached to either a carbon or a nitrogen that are adjacent to that environment. So looking at the methyl group here, adjacent to that environment is this environment, the CH2 environment. The same from here, that's why they're equivalent. So how many hydrogens are in this environment? There are 2. And the splitting is the number of hydrogens in those adjacent environments plus 1. So if I look at what's adjacent, it's 2 hydrogens. So the splitting pattern for this signal here would be n plus 1, would be 2 plus 1. So the splitting pattern would be 3, which means a triplet. If I look at the signal for this environment and I look at what's adjacent to it, if you've got an equivalent environment, then that doesn't count, right? So we're looking at different environments that are adjacent to, different hydrogen environments that are adjacent to our, what's producing our signal. So adjacent to the CH2 is a CH3, is a methyl group that has 3 hydrogens. Our splitting pattern is n plus 1, so number of hydrogens plus 1. So that is going to be 3 plus 1. 3 plus 1 is 4. So what we would see in our signal for our CH2 is it's split into a quartet. Let's have a look at another example. So you have to think, first of all, about how many unique environments you think there are, unique hydrogen environments there are. So maybe just pause the video. All right, so they are equivalent to each other. I'll talk through why that is in a second. We've got a hydrogen on in the OH group. We've got a hydrogen there, that's unique. And then finally, we've got this methyl group at the end. So this molecule would result in 4 signals. So thinking about why those methyl groups are the same, I could have drawn it slightly differently, and I think it would have been more obvious if I'd swapped when I drew it, this methyl group for this OH, so I'd move the OH to being here, would have been exactly the same molecule. I think you would have seen more clearly that there was a line of symmetry through the center of the molecule. But if we just think of it in terms of geography, if we start with this methyl group, what's next door is a carbon with a methyl and an OH, and then what's next door to that, carbon with a chlorine and a hydrogen. Start from here, what's next door? Carbon with a methyl and an OH, and then next door to that, carbon with a chlorine and a hydrogen, and so on. So these have exactly the same geography. Hopefully the other hydrogen environments are fairly obvious. If we're thinking then about the ratios, we've got 6 hydrogens, we've got 1 hydrogen, 3 hydrogens. So if I was writing the ratios, I would write that as 6 to 1 to 1 to 3. Okay, so in terms of my integration values, they would be in this proportion, 6 to 1 to 1 to 3. If I then think about splitting, when I look at the 2 methyl groups and I look at what's adjacent to them, it is a carbon, and attached to that carbon, attached to this carbon here, are no hydrogens. 0 hydrogens are attached to that carbon. So it means when I'm thinking about the splitting, I do n plus 1, and the number of hydrogens is 0, so it would just be 1. So they would produce a singlet. The thing to say about a hydrogen on an OH, or bonded to an oxygen, sorry, but an alcohol, a hydrogen, that is always a singlet. So that is never affected. A hydrogen on an OH group is never affected by anything on the atoms connected to the OH, and it never affects anything either. So the hydrogen in an OH group is just completely separate. You just think of it as a singlet. It doesn't affect anything else. It doesn't get affected by anything else. When I look at this hydrogen, it's attached to this carbon. So I look at what's next door. So there's a chlorine, so that's not got any hydrogens. There's a carbon without any hydrogens. But then there is a carbon with 3 hydrogens. So in total, next to our environment here, we have 3 hydrogens. So we would have n plus 1, 3 plus 1. That would mean we had, this signal gave a quartet. And then when we consider the final environment here, this methyl group, we look at what's next door. Well, it's just this carbon, and attached to this carbon is 1 hydrogen. So n plus 1, 1 plus 1 is 2. So we would get a doublet. So we would get 4 signals. The signal for, starting from left, the signal responsible for the 2 methyls would be a singlet. The signal for the hydrogen in the OH would be a singlet. The signal for the CH with the Cl attached, that would be a quartet, and then the one for the methyl group on the far right would be a doublet. And that singlet on the left would have an integration value or ratio of 6, and then it would be to 1 to 1 to 3. Now, I think the way to approach NMR in terms of interpreting spectra or interpreting the information that you're given is to think of it like a puzzle. And that's what you're trying to work out. You're trying to work out a puzzle. And what you're going to do is you're going to work out different parts separately and then put it all together to solve the puzzle. And fortunately for you, because this is A-level chemistry and they have a certain restriction on the size of molecules, so you're not really going to get anything that has more than 7 or 8 carbons. That means certain patterns recur, and you can look for these patterns. And if you look for these patterns, you'll begin to work out or understand the spectra so much faster. So I'm going to show you a table that I've made, and then I'll talk through it. But essentially, this table is there to highlight some of the patterns that appear in these NMR spectra. So working from the top, what this is really saying is that if you get a signal on the spectra, which is a singlet, and the integration value tells you that there are 9 hydrogens, then the fragment or the part of the molecule responsible for that can only be what I've drawn here. So if you see on your spectra a singlet with 9 hydrogens, you know straight away that one end of the molecule is this here. And so already, if you think about how many maximum number of carbons a molecule in A-level chemistry can be, you've already dealt with 4 carbons. I'm not going to go through every single one because you'll get the basic idea, the basic principle. What I want to highlight is the ones that are probably the most common. So this is a very common pattern, So you see a singlet and a singlet with 3 hydrogens. So that has to be a methyl group. That's how we get the 3 hydrogens. And the reason it's a singlet is that it will be attached to something that doesn't have any hydrogens attached to it. So how you then decide, well, which one of these is it? You know it's definitely a methyl group, but which one of these is it next to a carbonyl? Is it next to a singly bonded oxygen, and so on? That's when you look at the chemical shift. So the chemical shift will tell you whether you actually have a carbonyl attached to that methyl or whether you have a singly bonded oxygen attached to that methyl. So you've got, again, this is at one end of the molecule. You know now that you've got one end of the molecule if you see that. Another pattern that is extremely common, and you really, this is the one I would look for first, to be honest. So you've got to look at all of your signals, and I'm going to talk you through, working out what they mean shortly. Working out actual sort of example spectra. But if you see that you've got a triplet quartet, so you've got 2 signals, one of them's a triplet, one of them's a quartet, and you see that the triplet has 3 hydrogens and the quartet has 2 hydrogens, then straight away you know that is a ethyl group. And it's an ethyl group attached to something that doesn't have any hydrogens attached to it. And then again, to determine whether that ethyl group is attached to a carbonyl or a single bonded oxygen or whatever, you look at the signal that is the quartet with 2 hydrogens, and you look at the chemical shift for that, and that will tell you what it's attached to. And again, this is one end of a molecule, and having the ends of the molecule makes working the rest of it much easier. Now, quite often NMR questions are part of, are a significant part, but a part of a question, and in which earlier parts have been maybe about other analytic methods like infrared spectroscopy. So you might have been given a IR spectra and you've had to use the absorption information to work out, oh yes, there's a carbonyl, or oh yes, there's an OH group that's an alcohol, or an OH that's a carboxylic acid, or whatever. So if you know, for example, that you've got an OH, you can identify the signal that is the OH signal very quickly, because you will have a singlet with an integration value of just 1. So if you know that you've got an OH in your molecule, just look for a singlet with an integration value of 1, and you will know that signal is the one for the OH group. You'll see on your data sheet that they give quite a very broad range for the chemical shift, so really the chemical shift doesn't really help you when it comes to OH groups. And then the last one that I want to just talk about to highlight, just because it is more common than, say, some, is if you see that you have 2 triplets and that both of them have 2 hydrogens in those environments, then you will have a CH2. And then finally, I just want to go back to the triplet quartet one. Sometimes you will get a triplet quartet, but when you look at the integration values or the number of hydrogens, you discover it's actually 6,4, and that can throw you. But the thing to take from that is it almost certainly means that there are actually two ethyl groups. So just be prepared for that. One way to work that out is to count all of the hydrogens that you think you have based on the signals and see if that actually matches the molecular formula, the number of hydrogens in the molecular formula. I'll show you that in the questions that come up. But anyway, I would absolutely make your own copy of this table, and whilst you're getting used to NMR, I would use it. But of course, you're not going to have this in the real exam. So at some point, you have to put it away, and you just have to have grasped those certain patterns and look for those certain things. Always look for your triplet quartet. Always look for a singlet with 3 hydrogens. Always look for a singlet with 9 hydrogens. If you see those initially, you will have identified a large chunk of the structure, and then it's about a question of filling in the gaps. Okay, I think a lot of what I've been talking about will start to make much more sense as we work through an actual problem. So let's think about exam strategy, exam technique as well. And that's, in a sense, what I'm also trying to show you is how to approach problems like this to make them as easy as they can be. So they're telling us they're giving us a proton NMR spectrum and then they give us a molecular formula. And the first thing that the piece of information they give us is that there's a large peak at 1,705 centimeters to the -1. So that's its IR spectra. So we would use our data sheet to look that up and to see that that is clearly a carbonyl. All right, so we know that there's a carbonyl group in this compound. They then tell us that it does not react with sodium hydrogen carbonate, so it does not react with sodium hydrocarbonate or Tollens reagent. So what they're telling us there is it is not a carboxylic acid, and it is not an aldehyde. So we know there's a carbonyl group, but we know that that carbonyl group isn't a carboxylic acid, and it isn't in an aldehyde. So the next thing I'm going to look at is the integration values, which is going to help me work out how many hydrogens there are. So one of the things you'll notice is they're not just giving us a nice number like 3 and 1 and 6. They're giving us these values like 1.2, 5.4, 1.8. So we need to turn these into integers. We need to turn them into whole numbers. And what we're looking for is the highest common factor in all of these values. So what can we divide into all of these that will give us an integer, a whole number? And we're looking for the highest common factor. So 0.6 divides into all of these. So if I work from left to right, 0.6 into 1.2 is 2. The next one is 2 as well. 0.6 into 5.4 is 9. And then we've got 3. And then the next thing I would do before I move on is I would just add all of those together. So I've got 2 plus 2 is 4, plus 9 is 13, plus 3 is 16. And I would just then refer back to the original molecular formula and check that that is the same value, the same number of hydrogens that it says in the molecular formula. So I got 16. There are 16 hydrogens. That means there are definitely 2 hydrogens in this environment, 2 in this, 9 in this, 3 in this. Now, probably 90% of the time, these values that you work out will be exactly as it is in the molecular formula. Just occasionally, these values that you work out, they'll add up to perhaps half of what is in your molecular formula. So if they added up to half, what you would need to do is to realize that what you've worked out are the ratios, but the actual number of hydrogens in those environments would be double those ratios. But anyway, we've got the right number of hydrogens here. They add up to 16. There are 16 hydrogens in our starting molecule. The next thing I would do is I would write the splitting pattern. Now, you might say, or you might think, well, what's the point in that? You can see what it is, but I think writing it out, again, just makes seeing things that little bit easier. So again, working from left to right, that signal, the first signal has just one line in it, so that is a singlet. The second has 4 lines, that's a quartet. The third has just one line, that's a singlet. And then the final one is a triplet. Okay. Now, to me, certain things are already beginning to leap out. If we think back to that table I showed you on the, well, just before, we have a singlet with 9 hydrogens. That has to be, that can only be caused, sorry, by this. So we have already one end of our molecule. We've dealt with 4 of our 9 carbons. The other thing that also leaps out to me is that I have a triplet quartet, with the quartet having 2 hydrogens and the triplet having 3 hydrogens. That to me says that it is a ethyl group. And then to work out what it's attached to work out what it goes here, I'm going to look at the chemical shift for the quartet part of that group. So I look at that. Okay, it's not the easiest to read, but what is that? Maybe about 2.5. And that is most certainly within the range for a carbonyl. So that tells me that I have that. So the way I'd go about the next stage is I've got both ends of the molecule. So what I would do is I would draw those 2 ends with a gap in between them, and then I'd begin to think about, well, what is there left to use? How could I use that? So if you look at the green writing on the left there, I've got one end of the molecule, then I've got a gap. That's what I've got to work out still, and then I've got the other end of the molecule. So to help me work out that gap, the next thing I'm going to do is I'm going to do a tally of how many carbons and how many hydrogens and how many oxygens I've used out, and then see what's left from the molecular formula. So the molecular formula tells us that in the whole molecule there are 9 carbons, 16 hydrogens, 2 oxygens. So if I think about how many I've used of each, carbons I have used 1, 2, 3, 4, 5, 6, 7. So that means I have 2 left. Out of the hydrogens, I have used 3 plus 2 is 5, plus 9 is 14. So I have 2 hydrogens left, and then I have used 1 of the oxygens. So I have 2 carbons still to use, 2 hydrogens still to use, and 1 oxygen still to use. So the signal that I haven't said anything about yet is this. So it is a singlet, and it is 2 hydrogens. That means there's 2 hydrogens in the one environment, so it's got to be CH2. So if I then deducted 1 carbon and 2 hydrogens, I would be left with 1 carbon, 1 oxygen. So that tells me I've also got a carbonyl. So I've still got to fit into my structure now a carbonyl and a CH2. So I have a choice, right? I could, there are 2 possibilities. It could be that it's CH2 and then the carbonyl, or it could be the carbonyl and then CH2. Now, if you end up getting this the wrong way round, and but it has been this entire question that we've been looking at, this entire question or something equivalent to it in an AQA exam would probably be worth, well, let's say 8 marks. So if you get these the wrong way round, you will lose just 1 mark. But how could we know which it is? Now, this isn't actually an AQA question, so we've just got to be mindful that I think this is, if anything, ever so slightly harder than the worst you could possibly get in an AQA exam. So it's like sort of a worst case scenario. I think it helps us to look at the chemical shift. Now, the chemical shift for an environment that's next to a carbonyl is 2.1 to 2.6. But our CH2 here is above, well, it's above 3, isn't it? So that to me says that actually it's not going to be next to just one carbonyl, it's going to be next to two carbonyls. So that tells me that it's going to be CH2 and then C double bond O, then our carbonyl. When you see those chemical shifts on the data sheet, they are the shifts when the environment is simply next to that one other group, one other thing that affects the shift. It is, of course, possible to have an environment next to more than one group. And essentially the chemical shift, how much that shift or how great that shift is a reflection of the closeness of electronegative atoms atoms. So oxygen causes things to shift more greatly. Halogens cause things to shift more greatly. If we're between two carbonyls, we're going to get a much bigger shift than if we were next to just one carbonyl. That would explain why we have a chemical shift of above 3 when our data sheet says next to a carbonyl should be 2.1 to 2.6. Here we're next to two carbonyls. That would give a greater shift. But that, anyway, is now our full molecule. So the way we went about it is we looked for any immediate patterns that leapt out at us after we'd done thought about how many hydrogens and what's the splitting pattern. Straight away saw that this group had to be in the molecule. That gave us one end. Always look for a triplet quartet. They won't definitely be there, but there's a fair chance they'll be there. Look for your triplet quartet with the quartet having 2 hydrogens and the triplet 3. And then we used the chemical shift to work out that ethyl group was then next to a carbonyl. That then left us with just needing to sort out the middle bit, the bit between the two ends of the molecule. That could only consist of 2 carbons, 2 hydrogens, 1 oxygen, once we'd taken into account everything that we'd already used. Did a little bit of thinking. Could have got it wrong at that point, but we would have lost just 1 mark in total. And there we have our finished compound. So now we have another one to do. So they're not giving us any extra information here. They're just simply giving us a molecular formula. So there's nothing to tell us that there's definitely a carbonyl. There's nothing to tell us there's an alcohol, or whether it's a carboxylic acid or whatever. So we have to then deduce the whole thing from the information we're given in the spectra. So as before, let's think about the highest common factor that we can divide into all of these integration values. So we've got 0.8 and 1.2. There's only those 2 values to get whole integers. So 0.4 is the highest common factor. So we're going to get 2, 3, 2, 2, and then 3. Next thing then to do is to do the splitting patterns. So again, working from left to right, that is a triplet, that is a singlet, that is a triplet, that is a quartet, and that is a triplet. So, does anything leap out at us? Yes. Again, you have to have that table to hand that I showed you earlier, but having a singlet with 3 hydrogens, that tells me that is definitely a methyl group, and then it's going to be attached to something that doesn't have any hydrogens on it. And if we look at the chemical shift, it is above 3. We look on our data sheet, it can't be a carbonyl. It's going to be an oxygen like that. Okay, so we've got that signal. Then the other thing that leaps out at me is we have a triplet quartet. Now I appreciate there are 3 triplets on the spectra, so why is it that I've chosen the one furthest to the right? Well, if we're going to have that triplet quartet pattern, that ethyl pattern, then what we've got is we've got a methyl group, the CH3, attached to a CH2. So that means the chemical shift of that CH3, because it's only attached to a CH2, will be low. So that means this triplet must be the one that's involved in our CH3, CH2. So we've got then our CH3, CH2. Got to think about what it's bonded to and what it's attached to. We look at the chemical shift of the quartet. Was that about, I don't know, again, about 2.5. It would be much easier to read in a real exam question. But that is definitely therefore a carbonyl. So we've got two ends of our molecule. So I'm going to draw those so that one is one end and one is the other end, with a gap in between to try and work out what goes in between. I'm also going to do an audit. So how many carbons have I used? I've used 1, 2, 3, 4. So that means I have 2 carbons left. How many hydrogens have I used? I've used 3, 4, 5, 8. So that means I have 4 hydrogens left. And then how many oxygens have I used? I've used both. So I could probably just work it out, the fact I've got 2 carbons, 4 hydrogens, that it's got to be CH2, CH2. But there's also another clue, and maybe this would have allowed us to leap to the conclusion faster. But if you look at what the signals are left, we've got 2 triplets, each with 2 hydrogens. If you remember the table before, that has to be a CH2, CH2, where the 2 ends of that little group, that little fragment, can't be attached to anything with hydrogens attached. But as we can see, we've got oxygen and carbonyl at each end. That tells us that works perfectly. So there's our molecule. Okay, so I'm going to go through this a bit more quickly. The highest common factor that I could divide all of these integration values by is 0.3. So that would give me 1, 2, 3, 9. So add all of those up. 1 plus 2 plus 3, that's 6, plus 9 is 15. So if I look at the molecular formula, there are 15 hydrogens in the molecular formula. So that is exactly the number of hydrogens in each of these environments. If I look at the splitting pattern, I've got a quartet, I've got a singlet. Maybe that isn't so obvious, but it's a doublet. So one way of judging that is, if you remember what these integration values are supposed to be, is the area under the sort of lines. So the fact that we have more hydrogens in the one that's labelled 0.9 compared to 0.6, but it's not as tall, means that we must actually have more lines, because that makes up the difference in the area. And then finally we have a singlet. So leaping right out at me is this singlet with 9 hydrogens. It has to be, we've had it before, I'm not saying this means it's really common, but it's a thing to definitely look out for. That means we have that end of the molecule. Something else that leaps out, although this is less common, is that we have a quartet doublet. So you're going to have to refer back to the table, but we have a quartet doublet where the quartet is 1 and the doublet is 3. So we have this bit here. So what that, the group that refers to is, it must be like this. So this hydrogen is our 1 hydrogen, or one is this quartet with 1 hydrogen, and this methyl group here is this doublet with 3 hydrogens. So we have 2 ends of the molecule. So let's just write that out. So this is quite a large chemical shift. We're referring to this part of this environment here. It's quite a large chemical shift. I know that I've got a chlorine. I also know that I've got an oxygen, but this is beyond what I would expect for anything with that single oxygen. So that pretty much tells me that the chlorine must be here. So let's do our audit. So how many carbons have I used? I've used 1, 2, 3, 4, 5, 6. So that means I have 2 left. How many hydrogens have I used? I've used 3, 4, and then plus those 9, so that's 13. So I have 2 of those left. I haven't used any oxygens, and I have used my chlorine. So I've got 2 carbons, 2 hydrogens, and 1 oxygen to use. What signal have I not identified or done anything with? I've got a singlet with 2 hydrogens, so that's got to be CH2. And then that would leave me with a carbon and an oxygen, so that's got to be a carbonyl. So now I've got to work out which way round are they going to go. Now, the fact that this is a singlet, the CH2 is a singlet, means that the CH2 cannot be attached here, because if it was, I would get splitting because of this environment, the hydrogen in this environment here. So that means the carbonyl must go there. And then that means then I get my CH2. So there is no splitting for this CH2 because it's next to a carbon with no hydrogens, and it's next to a carbon with no hydrogens. And that is my final structure. And so we come to our final example. One thing to pay attention to in the description at the top is that it is an ester. So when we come to consider that the 2 oxygens, they're going to be an ester group. So as we've done before, what's our highest common factor? It's 0.5. So we would have 3, 2, 6, and 3. Let's add those up. So 3 plus 2 is 5, plus 6 is 11, plus 3 is 14, and there are 14 hydrogens, so that's all good. Splitting patterns, we have a singlet, we have a quartet, we have a singlet, and we have a triplet. So again, as we've done before, straight away, that tells me that that is a CH3, and then it is attached to something which is either a carbonyl or an oxygen or a carbon with no hydrogens attached to it. So I look at the signal, the chemical shift, and that chemical shift is about 2.1. So that tells me that that methyl group is attached to a carbonyl. I use my data sheet to realise that. So that's good. Other thing that leaps out, there's my good old trusty friend, triplet quartet. So that's our CH3, CH2. What is it attached to? Well, the chemical shift is below 2, so that isn't either a carbonyl or an oxygen. So that is a carbon where we have no hydrogens attached to that carbon. Now, if we look at this, it's a singlet with 6 hydrogens. So again, looking at the table, that has to be a carbon with CH3. And then if I just actually count up how many carbons I've used at this point, 1, 2, 3, 4, 5, 6, 7. Well, that's actually all of the carbons. How many oxygens have I used? Well, I've actually only used 1, but one of the things is that, and I should have probably have made a point of this earlier. I know it's an ester, so as soon as I had my carbonyl, I should have had my other oxygen there. So I've got both oxygens in my little fragments now. And then how many hydrogens have I got? I have got 3. So that's plus 6 is 9. Plus 5 is 14. So actually this is all of the parts of the molecule. This is one end. This is the other end. This is the middle. So my final structure must be... one thing I maybe should have done in all of these examples is, one way to do a final check is to work backwards. So once you've got your structure, once you've decided, I think this is my this is the molecule that's responsible for all those signals. One thing to do is to go back and imagine you were just given this, and you had to decide how many signals would there be, how many hydrogens would be in each environment or in each of the, responsible for each of those signals, and what would the splitting pattern be. So there's one environment, there's another, there's one, and there's another environment. So there would be 4 environments, so I should have 4 signals, and I do have 4 signals. In terms of the ratio of the hydrogens, well, it would be 3 to 6 to 2 to 3, which is what I've got. And then in terms of the splitting patterns, what would I get? Well, this environment isn't next door to any hydrogens, so that would be a singlet. This environment isn't next door to any hydrogens, so that would also be a singlet. This environment is next door to 3 hydrogens, so that would be n plus 1, 3 plus 1 is a quartet. And then our final one, or methyl here, is next door to 2 hydrogens, 2 plus 1 is 3, that would be a triplet. So that is in fact what our spectra shows. So this is not an exhaustive look at proton NMR. I haven't talked about any of the sort of basic recall facts like the solvent that needs to be used, or why we would use that solvent, or what the reference is, the tetramethylsilane being used as a reference. I've just really wanted to concentrate on how you could interpret the information you would get from a spectra. Sometimes they give you actual spectra like we've been doing here. Sometimes they give you a table of information where they tell you the integration value, or they tell you the number of hydrogens, and they tell you the chemical shift. And in effect, that's no different to what we've been doing. In fact, it's taken one step away really from you. You still look for your triplet quartets with 3 and 2 hydrogens. You still look for any of those other patterns. But I hope that's been useful. And if you've got any queries about proton NMR, then just let me know.